Physics, bro.
Hey.
So no one told you life was gonna be this way. Your job's a joke, you broke. Your love life's the way. It's like you're always stuck in
English physicist Sir Isaac Newton defined 3 laws of motion. His first law of motion stated that a body at rest remains at rest, while a body in motion remains in motion unless acted upon by an unbalanced force. His second law of motion stated that net force can be calculated by multiplying the mass of the object times its acceleration. His third law of motion states that for every action force, there is an equal and opposite reaction force. That's cool, but what does it all mean? Let's see a simple example.
I took a bowling class. I know this.
I bet you did.
I did, yeah.
I believe it.
2 sports boys are playing a game of backyard bowling. What forces are acting on the ball? The first force we add is the force due to gravity acting on the ball. Since the object has no vertical motion, we know that there must be an equal and opposite force according to Newton's third law acting upward. This force is called the normal force, or the force of the ground pushing up on the ball. We represent the ball moving right by drawing an arrow for the force applied pointing right. Because the ball is not rolling on a smooth, flat surface, we must add the resistant force of friction pointing left. Since the ball continues to move right, the force applied must be greater than the force of friction. These are represented by the size of the arrows. Now let's look at the ball's motion as it rolls to a stop. Now the only forces are the force of gravity of the ball pushing down on the earth and the normal force of the earth pushing up on the ball. There is no longer horizontal motion, so there is no longer a force of friction or a force applied. Let's see an example with vertical motion. A repeller makes her way down a sheer rock cliff. What are the forces acting on her? Let's start with the gravity of the Earth, which always points directly downwards. Since the repeller isn't in free fall, there must be a force pointing upwards. This upward force is the tension force of the rope. The repeller also exerts an applied force onto the cliff. Since there is no horizontal motion, the cliff pushes back with an equal and opposite normal force. Let's have a mathematician show us one final example. A person pulls on a 100-kilogram desk with a force of 150 newtons acting at a 30-degree angle above the horizontal. The desk does not budge. What is the frictional force and normal force? We will start this problem by drawing a force-body diagram showing all of the forces acting on the desk. We then write the 2 force summation equations. The first representing all of the forces in the x direction, and the second showing all the forces acting in the y direction. Since the applied force is acting at an angle, we must represent it in both the x and y directions. We now draw a right triangle breaking the applied forces into its x and y parts. We put the 30-degree angle in the bottom left-hand corner as represented by the force-body diagram. The 150 Newton force represents the hypotenuse of the triangle. The force in the x direction is calculated by multiplying 150 by the cosine of 30. The force in the y direction is calculated by multiplying 150 by the sine of 30. Now we will find the force of gravity using Newton's second law and the equation F equals ma. This means that we multiply 100 kilograms by the acceleration due to gravity, which is 10 meters per second squared, to get 1,000 newtons. Since we know that the force applied in the x direction minus the force of friction equals 0, we can set the force applied in the x direction to the force of friction. From this we find the force of friction to be 130 newtons. Now we plug in all of our known information into the force summation equation for the forces in the y direction. From this we find the normal force to be 925 newtons. There you have it, folks!
Slinking! Slinking!